we're going to avoid the math, the deep math, because as I said, it doesn't make sense to do the math and then explain the big picture. So essentially, what I'm going to do today is to introduce the technique of Kalman filtering, which is the most common technique used for localization. All aeroplanes, ships, anything that moves, boats, use Kalman filtering. So Kalman was an electrical engineer, originally from Hungary, and he died very recently in the US. Became famous because of his Kalman filtering algorithm. Something that is used in all navigation forms. So yesterday, I think we went through all of this. Yeah, we went through all of this and this one and this one. I know exactly where I stopped because I was telling you that you can do SLAM with Bluetooth. So if you have odometry and there are Bluetooth sources, like every cell phone is a Bluetooth source. So it is possible in a room to locate someone accurately with odometry as well as locate a robotics with Bluetooth and odometry. And we also, I pointed out the two classic papers on, this is the guy who came up with SLAM, Hugh Durant White and Tim Bailey. Okay. So, we are going to discuss the challenges of localization because it's not a problem that's going to be solved anytime soon. First of all, you can't get 100% accuracy. Nothing is 100% accurate in the real world. But also, it's a problem where the accuracy has to be incrementally improved. Some applications need higher accuracy than others. And the example I gave you was that if you have if you have a robot navigating a minefield, the accuracy is something different than a robot going down the hallway. Similarly, if a robot is going next to a swimming pool and it's not waterproof, then it's got to be extremely accurate in its localization because it can't fall into the water. So, the question is, how do you determine the absolute pose of the robot, right? Now, GPS can be used outdoors, but there's no GPS indoors, except that, we talked about some of the problems of GPS outdoors also, such as, you can have outages, and you can have outages that are actively caused by countries nowadays. They're all preparing, if there's a war, that they want to black out the GPS of the opposing country. So, Elon Musk has all these satellites, Starlink system, so many satellites, and yesterday somebody in Russia was saying that we know a way of knocking out all of those immediately. So outages are possible in that context, but not in a normal context anymore because there are too many satellites. And then of course, inside a tunnel, you can't get a GPS signal, so you have to do without it. If you're using it to localize, then temporarily it won't be available. You got to do something else, follow the walls of the tunnel, and then when you get out of the tunnel, pick it up again. In New York City, the GPS signal becomes unreliable because of the multi-path phenomena, bouncing off, many of those tall buildings. And then you have this problem that GPS by itself is not accurate enough. You have to do something extra with it to make it accurate. The original GPS was like a meter or more. If you needed to take an exit from a highway, 1 meter, 5 meters, even 10 meters might be enough. But for other applications, it was not accurate enough. And of course, the repetition rate or the sample rate is 1 hertz. So if you're going at 200 miles per hour, then 1 hertz is not going to be enough. If you're going at 50 miles per hour, it might be enough. So everything is relative. A number is not instantaneously good. It is in the context of what application are you using it. Now, you'd be surprised, I started to say that and then I looked at this bullet. So you'd be surprised that there are indoor location systems available now. Now these companies might be out of business. I checked a couple of years ago, Stargazer and Cricket. So they are a means of creating a GPS-like system indoors. Now, where would they use it? So typically, in cases where you need to monitor patients with Alzheimer's or even children, because you want to give children and even people with Alzheimer's some freedom. You don't want to tie them down or handcuff them to wheelchair, because that affects the quality of life. So you want them to wander in the grounds of the facility, but not exit the gate and walk across a road with fast moving cars. So they have this system whereby they're being monitored, and if they get out of the building, then there'll be an alert. And the way they do that is they all wear tags. These patients and children, the same thing. You know, dogs have tags nowadays. Even cattle are given tags, because you don't want the cattle to wander away in the farm. So they do have an indoor system. It's based on you know, beacons. So you have local beacons, and those beacons typically cover only like 10 or 50 meters, or rather 40 to 50 meters, and then you have to repeat them periodically. So it's very expensive. So what they're doing nowadays is they are designing these things in it for certain buildings. It's easier when you construct the building to add these on rather than retrofit it. Retrofitting always takes more money. So that's what they're doing in many of these hospital facilities. Now in Detroit we have a printing facility, relatively new, and they have deliberately organized the ceiling lights in a pattern. So the robot is looking up, and you know, when you look up, the chances are that your view will not be obstructed, because nobody's going to be hanging in the area. So they've designed the plant so that the robot can count the number of lights and use that to localize itself. So since GPS is unreliable, or indoors it might not be available, and you may not have a cricket system or stargazer, you're going to have to use landmarks. I don't know whether I mentioned this yesterday, but if you have a long hallway in your house, then basically you don't have any features. But the moment you hang pictures, right? Not the same picture. If you hang the same picture multiple times, then you'll get confused. But if you hang different pictures, then you can create landmarks for yourself. And that helps in localization. And then comes this big problem, which is, are you just happy with localization, or do you want to map and localize? You know, remember localization and mapping? So this is a much more difficult task than people realize, because to really create a good map, you need fairly accurate localization. I think I briefly mentioned this yesterday. The big problem is the turn error. If you think you're facing here, but you're actually facing here, you're going to put whatever you see here, right? And you're going to do it in the rest of your motion. You're going to constantly do it. And if you look at that map, it'll be like people threw down walls that were connected or no longer connected. They are at an angle, and everything will be like mixed up. So you have to be able to localize accurately, reasonably accurately. You cannot get 100% accuracy. So in a competition, we once tried that, because that competition is made up of multiple heats. So if on the first heat you went 50% of the way, right? And you get a map of that, the next time you can drive in the map. You don't have to worry about identifying obstacles and so on. It was so difficult to build a map. So basically we ended up by not being able to do it, because the map was all over the place. It was putting barrels in the wrong place, and that's as good as not having a map. It's better to assume that you don't have a map. If you have such a scrambled map, if your mapping algorithm is not good, you'll end up by blocking your path with ghost obstacles, because you'll be putting obstacles everywhere and you'll be blocking your way. So it's better not to do bad mapping. It's better, just to say, I'll run without a map. So this is the challenge of localization, implementation. So over there I was talking about challenge of localization on a conceptual level, but now we get to the implementation phase. Now these are some things that even as medical robotics students, these are life's lessons, by the way, for any engineer. So you'll find this a good revelation, because when I was a young student, I didn't realize this. I thought a sensor is perfect, it should give you the exact result. That's why, you're paying money for it. Not so. They all have a big data sheet listing under which conditions they work and what accuracies you can expect. So sensor noise is a phenomena that you often run into, which really means the genuine information is paired with noise. Noise is sitting on top of genuine information. Now here are some examples. The same scene. You haven't moved the camera. but clouds came over. So it's the same scene, but cloudy conditions are better for image processing compared to sunny, because sunny you get reflections, right? You get the sun, well, the low sun at sunset or dawn is the worst possible thing for a camera, but even for the human eye, right? But the human eye has the power to adjust. Most cameras, maybe they are getting better now, don't have the power to adjust. If the sun is directly in the eye, and even human beings, when somebody shines a light in your eye, you can't drive anymore, right? But cameras fail even earlier than that, because they are not biological. You know, our eyes are biological and have some compensatory mechanism, but commercial sensors don't. So you're looking at a scene and there's a raindrop, or somebody just touches your lens with a greasy finger. So that can be considered as noise. You know, nothing has changed, the scene has not changed, but now you see something different, right? What about sensor mount vibration? You have mounted the sensor and there's a loose screw and it's going like this. So the scene is going to be shaking. It's the same scene, but there is some noise added to it. So how do you overcome that? As a human being, we have this problem when driving in bad weather, right? But we have so much extra information coming in that we are able to find the truth somehow. We have multiple things going on. And of course, there are situations where even a human being has to stop and say, okay, let me wait for the rain to stop, right? But long before that, the machine will come to a stop, because it doesn't have this ability that the brain has, you know, to put together multiple information. So what we are doing when you're writing algorithms is to attempt to reproduce the brain. We're making a bad attempt to reproduce the brain, and it's getting better and better, but not fast enough to represent a human being. And of course, you have to wonder, if it does become like a human being, what does it mean for real human beings, right? Are these machines going to take over? That's the debate that's going on. That if they keep on improving and they become as good as a human being, then what? And all of you have heard about ChatGPT, right? So ChatGPT knows so much more than us, because it never forgets, right? And the beauty is, if one computer learns, like, how long does it take for you to teach a language to a new person? Many, many hours, right? Even if I have a class, I teach the class and then I will teach another class, right? It's a linear process, right? I teach 25 the next semester. But once one computer knows, all computers know. So that is the fear, that the learning is like that for a computer. For a human being, it's many hours of work that has to be repeated again. So ChatGPT has already got so much information in its head. It makes mistakes, but it's got more going for it than many human beings, like maybe all human beings. So God knows what's going to be the next step. Okay, the second challenge of localization on the implementation front is sensor aliasing. I'm not sure whether you heard the word before, but aliasing means basically you're somebody trying to pass themselves off as someone else. That's what aliasing means. So how does that come in this particular case? So any object that we see is not unique. See, all the chairs look alike. So let's say that you're going down a dark hallway. All the doors typically look alike in newer buildings. You know, they're designed to be exactly the same. So if a robot sees a door and another door, it can't tell the difference. That's called aliasing. Now, a human being might have a way of separating them because there are other rules going on in our head. But a robot sees a door, it looks exactly like a door further down, it's going to have this problem of not being able to tell which door it is. Now, of course, if the person's nameplate is hung there, it's different. But just a door, they all look alike. Many restaurants have the, you know, McDonald's looks the same. You know, they design it that way. All McDonald's look alike. It's more true in the Western countries than here. That, you know, the franchises look exactly the same. So traffic barrels look alike. Do you know what a maze is? So a maze is designed to take advantage of this aspect that, you know, all mazes look alike. I'm going to put the picture up as soon as I can bring it up. So this is a nice test for a robot. Okay. And the reason is, show it, I think. No? I lost my entire screen. One second. Okay, you see, amaze. Right? So, in Western countries, they have a physical creation of this maze, not just on paper, but they have a physical creation of this maze. So all the edges are cut exactly identical, and you know that what the rule is to solve a maze. The one rule is keep taking the right. You know, there may be more optimal algorithms, but one rule that will definitely work apparently is go right, or left, and eventually you'll find the opening. See the opening? You need to get out of this. So they have mazes, physical, so that you can't see over the top of them. The mazes are taller than the tallest person. And it creates a lot of panic in some human beings because it's supposed to be fun, but when they can't get out after 20 minutes, some of them actually get panicky and pass out or start yelling. So they do have a guard tower, right? From there they're watching. And if you get into that state, I mean, you can't imagine why people would do that, but there are actually people who, you know, get panicky and claustrophobic. Then the guy in the guard tower would yell out instructions. He'd say, go right, go left, to get them out. Because he can see everything, right? He can see the whole map. They can't. So you see the point? The person inside, the map is useless because everything looks alike. The person outside, they can see everything and where the person is who's yelling now. So it's a good example of, you know, why you need localization, because, you know, otherwise you'll never be able to get out of this. Now, actuator noise. Now, this is probably something that you never thought, but I didn't either. So if you have robot motors, right, and it stopped, and you give it a certain command, right, it goes like this. Then you pull it back. You give it the same command. Do you think it's going to end up in the same position? If you repeat the same command 10 times, will it end up in the same position? And the answer is no, because first of all, there is this randomness in the real world. But secondly, the battery, right? The charge of the battery, like the more the battery discharges, you won't get the same torque for the same command. And because you won't get the same torque for the same command, you're going to end up in slightly different positions. So that's why in the real world, we drive with feedback. We don't just, you know, go for a certain, this is the homework you're going to work on next, right? We don't drive for a certain time. We actually see whether we made it there. So that's why, that's how you overcome actuator noise. You call that noise in the sense that you issue the same command, but it ends up in different places, right? That's called noise. Because there is some ideal place, and there are all these other places that you get. So you can think of it as random around the ideal, you know, motion. It could be the ground under tires. Maybe on a different day, the tires are slightly underinflated. It could be any one of those factors. On the same day, it might happen. Maybe it's a little bit warmer now. So, you know, when it warms up, the tire pressure increases, right? So it could be that. So that's called like actuator noise, and that's why feedback is so important. Feedback is important in most things in life, but definitely in robotic motion or robot motion, it is definitely important. Now, so we already talked about this when we first brought up odometry, but I'll just refresh your memory on this. So odometry is using wheel rotation sensors. I believe I may have shown you a picture of an encoder, right? It's basically has these alternate black and white sectors and the wheel. And so when the wheel rotates, a beam of light is interrupted by these black and white sectors, and you can count the number of pulses. So counting the number of pulses is fine, but isn't there a difference between 2,500 pulses around the circumference and 5,000? Because 5,000 is enabling you to measure the rollout of the wheel, what? Half the distance compared to the 2,500. So if you're turning right in the middle of one tick of the encoder and the next, then basically, is it the previous tick or the next tick, right? Well, obviously you're going to go with the previous tick, right? But if you put more takes, then maybe you will get another take, right? And therefore you'll be more accurate. So therefore, odometry, you see, for this one reason, it can't be accurate. Because it might turn in the middle of 2 takes. And there's no way you can actually measure that because you only have a certain number of takes. It won't solve the problem if you have 1,000,000 takes. It'll make the product more costly because your pulses are now coming in so fast, you have to process it, but you still have a problem of localization. So that's called finite encoder resolution. Wheel mismatch. One tire inflated more than the other. So even if you drive it at the same speed, you'll actually be turning. So if my right tire is overinflated, I'll be turning this way when I ask you to go straight. If my left tire is overinflated, I'll be going this way when I ask you to go straight. So this happens with all vehicles that have tires, even new cars, I told you. And there's the question of slip. So even when you think you're not slipping, you actually are. You just can't, you don't notice it. So you'll notice it more when there's ice, but even on regular terrain, there are little micro slips that are going on. And you know, a micro slip means that you get encoder count, but you haven't moved. So that means that there'll be error. Now, the problem is these position errors, they accumulate. They add on, they don't cancel out. They keep on adding on. And if you don't correct it periodically, that's the old example, counting the steps, right? At some point you have to look up and say, okay, I'm at the end of the hallway. Now, it seems silly me saying that because we do it automatically, but to get a computer to do what a human being does is a big, task. So we have to think of it as a human being counting steps and then looking at the scenery to see, did I make it to the parking lot? Am I going in the right direction? So you use visual feedback to check whether your steps are taking you in the right direction. So the blind person is the best example of that. A blind person would also be lost, but you know what a blind person does in their apartment? First of all, they organize the furniture in a certain way and get used to it. If you move that furniture around, you're going to screw up a blind person's system completely because they depend on that, like a familiar sofa. So they grab onto it, the door of the refrigerator, right? Or the door to the bedroom. That's how the steps, the odometry is the steps, and then they correct it by that GPS, their own GPS, which is, grab something that is familiar. So there are 3 types of error because of the odometry problems. One is range error. What is the total distance you have traveled? That is the most favorable of the 3 errors. That error takes the longest to fall apart. So even with slips and all the other problems, your typical total distance recorded per odometry will have the smallest amount of error. So generally it survives longer. The culprit is the turn error. Because the moment you get this slip, you think you're facing here, but no, you're not facing there. You just slipped, but you're still facing here. So imagine, you think you're looking here, but now you're looking here. Now, if you proceed on these 2 diverging, you can never recover from this. Because now you think you're pointing here, but you're pointing here. But now these 2 paths are going to, from that point onwards, they're going to, go fall apart, diverge. So that's why the turn error is deadly. And if you have more turn error, the odometry will fall apart sooner, and you'll be praying for GPS or some other form of correction. And drift error is the accumulation of the turn error. So turn error accumulates, and that's called drift. So it's definitely not self-correcting. It won't correct itself, You actually become worse and worse. So you'll see in the form of an experimental study exactly what happens to it. Okay, so by the way, I just told you that turn error is the worst possible thing that can happen to you. That's why sometimes people add heading sensors. Not quite GPS, right? But heading sensors like a compass. So you can immediately correct because the compass will still point in this direction, right? So if you feel keeping odometry alive longer is more important to you, then they add a compass to it. And a compass will compensate for turn error. So in this book, which is a popular autonomous mobility robotics book, this guy Siegwart is from one of the top robotics schools in Europe, ETH Zurich in Switzerland. He did a study whereby, but actually I think it's from his book, but it's not his study. So these figures are produced from that study, and there are two of them. The next one is on the next slide. So let me explain what this is. I don't know what your exposure is to probability, but I'm going to explain it to you intuitively. So, you know, many things in life are governed by the Gaussian distribution, also known as the normal distribution. So like heights of students in this class, right? There's going to be a spread, and typically it will fit a Gaussian. If I pick you up, turn you upside down and shake all the change out of you, we'll get a distribution, right? There's going to be very few people with 1 crore in their pocket. I don't know, maybe you. So there'll be very few at the two extremes, or zero. But there'll be a lot more in the middle, right? And that's what the Gaussian is. It sort of represents the law of life. Most things, not all things are Gaussian distributed. Most things are. The point when we die, right? Definitely Gaussian. So sigma is the standard deviation of the distribution. And then you also have a mean. In this case, it happens to be 0. It doesn't have to be 0. It can be anything else. But you have a mean of 0. And this is 1 sigma. And this is 2 sigma. There is a probability that you can get infinity. There is a probability. But the chances are low. So you can get a point way out on the other side or way out on this side, right? But the chances are very little, you know. So what is the probability that a person is 15 feet tall, right? I haven't seen anybody, and you know, is there anybody living like that? Probably not. So all the extremes live on the wings of the Gaussian, right? The chances are not much. Okay, now this is a two-dimensional Gaussian. So if you have two variables, x and y, the robot position is after all x and y, then you have to characterize the uncertainty of the robot's position by a two-dimensional Gaussian, if you want to use a Gaussian to characterize it. Okay, now that's what is going on here. So the pose uncertainty. Pose is not one number, it's not two numbers, it's three numbers, x, y, theta, right? So here, the robot is asked to drive a straight line path. And it starts off with absolute certainty. You know where you are because you used some super GPS initially. And then you use odometry from that point onwards and see what happens. So this is a two-dimensional Gaussian. It's just drawn that ellipse to show you a two-dimensional Gaussian. In other words, it's a projection, it's a section of this. Maybe at 3 sigma. So imagine if you have a 3 sigma cut, right? Because remember, 1 sigma cut for a one-dimensional Gaussian is here. Similarly, for two-dimensional, you have to do two of them, right? So he's doing a 3 sigma cut, and what does it show? Remember I told you the range error is the least? Well, see, the Gaussian is not growing much in this direction, right? So the uncertainty is not growing very fast in this direction. This way it's growing quite quickly. What is the reason for that? The turn error. So basically it says there is a chance it could be here, or here, or here, or here, or here, or here. And that chance seems to be expanding sideways as you go. So that's what I meant. Odometry is going to fall apart. And the turn error is the culprit. Range error is fine because it's compressed this way, it's expanded out this way. That's the problem with it. Now, this is this old circle. So he gets the robot to move in a circle, and this time the ellipse is like this, getting bigger and bigger. Something odd is happening here. You would think that it would grow perpendicular to the path, but here's a comment here that says, note that the main axis of the uncertainty ellipse, the main axis is this way, does not remain perpendicular to the direction of movement. Now, I have the same question. How come? Shouldn't it be perpendicular? To answer that, you have to go to the original research paper and find out why. So, this plot is coming from a research paper from that book. But the point is, it's getting more uncertain this way, not that uncertain this way. So, that is the problem with odometry. That turn kills you. If you don't get the turns locked down, the map will be all over the place. The map will be useless. So, odometry is not good enough. It's going to need help, right? We know that. It's like counting steps, and then you have to look up. Every once in a while. You don't have to look up constantly, though human beings do. Actually, we don't do that, We look at our cell phones a lot these days. So, have you heard about these stories of people looking at their cell phones, walking down a sidewalk, and running into a pole? Very true. So, is that localization error or just stupidity? So it could be stupidity because they don't have a map of the environment in their heads, right? So they're just counting steps in their heads and walking, looking at the cell phone, and they hit a pole. There have been people who have stepped into traffic and got killed. Like they don't realize that it's a red, and they walk right off and they get hit by a car. So you need help. So what is this help? GPS is the easiest way to do it. Indoors there's no GPS. You can also do IMU. So IMU replaces odometry for skid steer vehicles. So for vehicles that move without rolling tires, right? Well, skid steer vehicles also roll, but when you turn, they have to skid. Because how do you get from here to here when you don't have a steering wheel? You have to run the left wheels faster than the right and you skid this way, just like a tank. Some people use IMU and odometry because remember, redundancy is good. So some people, they want a good localization system. So they add an IMU even though they have odometry. So then you have a three-way fusion of information. IMU, odometry, and GPS. And then LiDAR is, I talked to you about it, I believe yesterday, that LiDAR enables you to pick up the obstacles, and as you move, if you can figure out what those obstacles are in the new position, then you have a way of correcting your location. So that was the original SLAM, by the way. That was what was called SLAM, but now they have vSLAM, video-based SLAM, Bluetooth SLAM, wireless SLAM, all kinds of SLAM now. So there was the story of a lady in the middle of winter in Montana. She went off the road, snow everywhere, and was in the ditch. And she had not told any of her family or friends, where she was going. And they located her just from the Wi-Fi signal. So that is a kind of a Wi-Fi SLAM in a way, because they found her before she died, because the cold would have killed her. They located her purely from her cell phone, the signal to the towers. Now we're going to watch this. We just watched it a couple of times already, right? But it's a very nice video that illustrates the concept of SLAM. Now, I keep telling you this. If you get into the math, then you're going to commit suicide. So the math should come later, maybe much, much later. You have to understand the concept first of what the SLAM is. So let's play this video. That's not the one. What is it doing? This is a CNN. This happened to me a couple of times yesterday and I couldn't figure it out. That, and this morning I tried it, it gave me the right one. Now it's a CNN news item. So I'm going to cut and paste it this time. So let me, or maybe I'll just Google it, because it might do the same thing. Yeah.
In the last video, we talked about how we can estimate an autonomous vehicle's pose, that's its location and orientation, if we already had a model or a map of the environment. In this video, we're not going to have a map ahead of time. We're going to have to build one while simultaneously figuring out where the vehicle is within that map using a process called SLAM, Simultaneous Localization and Mapping. There are many different SLAM algorithms, but they can mostly be classified into two groups, filtering and smoothing. Filtering, like the extended Kalman filter or the particle filter, models the problem as an online state estimation, where the robot state, and maybe part of the environment, is updated on the go as new measurements become available. On the other hand, smoothing techniques estimate the full robot trajectories from the complete set of measurements, not just the new measurements. And understanding these methods can be more intuitive if we address them under a graph-based formula.
So let me give you a little bit of background. So this was a classical technique, which is what I was describing to you yesterday in class. So you keep going, the barrels move, right? And every time you get a LiDAR view of the barrels, you again correct your position, right? Because you've seen them from a different position. Photometry tells you how far you've moved. You take new readings using a LiDAR of these very same obstacles, and using that you're able to correct your position, right? So you never return back to things you've seen before. So that's the filtering method. So the problem with that is you have something, we already used the word drift. The error, even though it grows slower than with odometry alone, does grow. So it keeps growing. So the second method that is going to talk about uses a method known as post-graph optimization. That method is known as the smoothing method. But it requires you to revisit the parts of the environment that you have seen already. Now you can see, this is one of life's trade-offs, right? Life is full of trade-offs. You won't get something for nothing. You always have to give up something to get something better, right? So what is the problem with going back to previous areas? You know, if you're in a battlefield and you're developing a map as you go, you don't have the time or the luxury to go back and make your SLAM more accurate. You have to keep going. So you're forced to use the filtering method. This requires you to revisit areas that you've already been in. So in an earthquake, you know, when people are dying, you're not going to even have the time to do that. Yet it's a better method if you have time. And apparently most people use this method, you know, provided they have the time, of course. So let's continue.
Simulation. In fact, in recent years, one particular framework, post-graph optimization, or more generically, factor graph optimization, has become the de facto standard for most modern SLAM software solutions. So in this video, we're going to focus on understanding what post-graph optimization is and why it works. So I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. Let's set up the problem. We have an autonomous vehicle, a robot, that has the ability to move through an environment. We've given it LiDAR to sense the distances and angles to nearby obstacles, and we've given it a way to dead reckon its relative position over time using odometry. In this case, it uses wheel encoders to count the number of rotations each wheel makes as it drives, and from that it estimates how far it's gone and how it's turned since its last known position. So the question is, how can we use these sensors to understand what the environment map looks like and figure out the robot's pose over time? Well, let's start with a simple mapping problem. Here I've placed the robot in a rectangular room with a circular obstacle in the corner. We can see this map and see where the robot is, but it has no idea of either. To it, it's just in an unknown void. Let's start with a very ideal situation, one in which there is no uncertainty or errors in the LiDAR or odometry measurements. They're just perfect.
So that's not possible, right? So he's assuming that just to make a point. You'll see how easy mapping is now in that scenario.
Right. In this situation, developing a map of the environment is relatively trivial. The robot could take a LiDAR measurement, and we'd have confidence that what it measured is the real obstacle location. It could save that off in a global map and then continue on. After driving some distance, which again precisely because of the perfect odometry, it takes another measurement. Now, the two measurements will align nicely in the global map since there are no errors in our system, and in this way we can just keep driving all around the environment and create a perfect map, all while knowing exactly where we are at all times. Of course, this scenario isn't realistic. There's error in both the LiDAR measurement and in the odometry, so there's some uncertainty in the estimated robot pose and in the distances to the measured objects. So let's try to map this room one more time. But this time we'll say that the LiDAR is still...
So green is the true position. The other one, gray, is the odometry position.
pretty accurate, but there's a large uncertainty in the odometry measurements. I don't know, maybe one of the wheels keeps slipping, so the robot thinks it's moving in a different direction than it actually is. So let's see how this works out for our robot. We get an initial LiDAR measurement, and we assume that there's an obstacle there just like before, and then we drive a little bit. Except this time, the estimated pose is different than the real pose. So the LiDAR returns some relative distances to the wall that the real robot sees, but we can only assume that it's relative to the estimated robot pose, since that's all we know. This places the two measured obstacles in different frames, and not a global environment frame, so they don't line up. If we continue this process, as we drive the robot around the room, the error in odometry causes our estimated pose to deviate more from the real pose, and what we're left with in the end is this map of obstacles that doesn't resemble the real environment. So this is one of the reasons why we can't just take measurements of the environment and stick the results into a map. Uncertainty in our system is going to mess it up. But this is where SLAM algorithms can help us. As I said at the beginning, in this video we're going to focus on pose graph optimization. I want to provide a little intuition behind the algorithm and give you a feeling for how it works without a bunch of math. But if you want to learn more about the mathematics, I've left some great resources in the description that go through it in detail. Just like before, we have our real and estimated robot poses, which at the beginning lie right on top of each other in the real environment map. But now on the right, there's also this blank area, and this is where we're going to build up the pose graph. The first thing our robot does is take a measurement of the environment. This measurement is associated with the current estimated robot pose, and we can add both to the pose graph. So essentially what we're doing is saying that this pose is defined as an X and Y location and a rotation angle. And along with it, we save off the distances and angles to the sensed obstacle.
So he's saving both the odometry pose as well as the view. So it's a lot of memory. And you have to do a lot of calculations, right? We're not doing the calculations, but you'll understand the concept when he finishes up.
Now, there's also uncertainties associated with this pose entry, but I'll get to that in a second. All right, so we have our first entry in the pose graph, so let's get the second. Again, the robot drives for a little bit, and our estimated pose starts to deviate from the real pose. Another measurement of the environment, which gets associated with the new estimated pose, and this combination is now saved in the pose graph. So we have two poses, each with their own local estimate of where the obstacles are. And even though we don't know where these two poses are in the environment, we do have an idea of about how far apart they are from each other. In our case, this knowledge came from counting the wheel rotations. But the idea behind this SLAM algorithm isn't tied to a specific set of sensors. The relative pose distances could have come from another internal measurement source, like an IMU, or we could have figured out how far the robot moved from other external sources, like GPS or visible odometry. The point is that we have some best guess as to how far away these two poses are from each other, as well as a measure of how confident we are in that guess. In this way, there's a constraint that we can place on the relative distance between these two poses. Ideally, they would stay exactly this far apart, since that's our best estimate. But due to our uncertainty in the odometry process, maybe we'd be better off if we moved these two poses around relative to each other. For example, it would be nice if there was a mechanism that would be able to move the two poses around to align the currently misaligned obstacles. Well, there is. And the constraints are the key to doing it. To visualize a constraint, I think it's helpful to imagine a rubber bar connecting the two poses. The nominal length of the bar is how far apart we estimate them to be. And with no external forces on these poses, the bar will just keep them at this fixed distance. However, if I hold one pose fixed and move the other pose closer to or further from it, it will compress or stretch the rubber bar, and there will be a force that wants to restore the poses back to their nominal distance. And the strength of the rubber bar depends on how confident we are in the distance estimate. If we have more confidence, or we have a really good odometry process, then this is a really strong bar that makes it difficult to change this nominal distance. If we have almost no confidence, then this rubber bar is very weak and provides almost no restoring force. So in pose graph nomenclature, we say that the poses are the nodes of the graph, and the constraint, or the rubber bar, is an edge. Of course, this constraint acts in all three pose dimensions, both x and y, and in rotation, always trying to bring it back to its estimated distance. All right, so there's not much we can do with two nodes and one edge, so let's keep going. Just like before, the robot keeps driving along and measuring the environment. And after a measurement, we can take the estimated pose, along with its measurement of the local obstacles, and place it in our pose graph and add a constraint. So now we have three nodes and two edges, and we can continue this, filling out our pose graph one pose at a time until we have something that looks like that incorrect map that we built earlier, with the exception that there are these constraints connecting all of the poses together. We still can't do much with this information because you can imagine that all of the bars are at their nominal length and everything wants to stay right where it is. However, we're at a point where something interesting can happen. Our first pose and the current pose are both observing the same feature in the environment. This means that we can build a new edge, a new constraint between these two nodes. We just need to understand how these two features align to figure out where the two poses have to be relative to each other. And in this example, they would have to be in the exact same location. So now we can add a new constraint, one that connects the first and last poses together and closes the loop. This bar has a nominal length of 0, since these two poses want to be right on top of each other. And the strength of this rubber bar depends on how confident you are in your external measurements and your ability to associate the two sets of data as the same feature. If you're really confident, like we are in this example, this bar is extremely strong. It really wants to pull these two poses together. So hopefully you can start to see that a loop closure is the thing that makes all of this work. Without a closure, all of the constraints were just happily being met. But with a loop closure, we have a way to inject tension into this graph. The blue bar wants to pull those two nodes together, and the purple bars all want to keep the relative distances the way that they are. And so allowing this graph to settle to equilibrium.
So you see what's going on? He's not just making this the same as this. He has to figure out what are you going to do with all the other positions also. And the algorithm allows you to do that. Because you know that this and this are essentially the same because you're looking at the same obstacle, you have to adjust all of them, not just the closest two links.
Or to balance all of the forces that each of the constraints are imposing is the optimization part of pose graph optimization. And what's really cool about this is that by optimizing the pose graph, not only do we have a better estimate of the current pose and a better model of the environment, but we also have a better estimate of where the robot was in the past, since all of the past poses were updated as well. So we got a lot of value from this one loop closure. Of course, you can see that we don't have a perfect model of the environment or the robot poses, but that's okay because we can continue to improve our estimate by making more loop closures. The robot can continue to drive, adding new poses from odometry and new loop closures wherever it's able to determine a relationship using external data. And for this example, let's assume we were able to relate these three poses together, even though this area of the room is relatively featureless. At this point, all of the previous constraints are the same as they were before, and until until we added these loop closures, the graph was still in equilibrium. But now we've added new loop closures, and this has created more tension, which wants to tug and push on all of the other poses a little bit, and so we need to rerun the optimization again and allow the graph to resettle. In this way, you can see how after each loop closure, the graph will continue to improve its global model of the environment and the past robot poses. That is, as long as the two poses that you connect are truly looking at the same environment feature. If you make an incorrect association and you build an edge with a constraint that is not real, you can imagine how this would persist in your graph and continue to skew your optimization process every time you run it.
So what he's explaining here is, remember I told you about doors that look alike, sensor aliasing? So you run the risk of thinking you're looking at the same scene, but maybe because it's a similar barrel, you made a mistake. So once you throw in that piece of data, it's actually going to go the other way. You're going to lose accuracy. So he's saying be careful. If you're not sure, he says don't add the new scene, just skip it. So it's better to be sure is what he's saying before you do the loop closing over and over again. So it's not an easy problem, but we don't have to have 100% accuracy to succeed. We just have to have good accuracy for the mission you're doing. So it's always the case, engineering systems are built for a mission.
It would always be pulling those nodes in a direction away from the truth. So it's incredibly important that you are confident in any loop closures that you make. In fact, it's better to miss a real loop closure than it is to add a false one. You can always drive around some more and make another closure in the future, but it's harder to remove the bad ones once they're in. Now, it's also important to note that a loop closure requires an absolute measurement of the environment, like we got with LiDAR, or you could get with a visible camera or some other environment sensor. You can't close the loop using a relative sensor like an IMU or the wheel encoders, because there's no way to relate that information back to an older pose. You may think you're near a past node, but without checking the environment, you can't know for sure. Okay, so we have our pose graph and we've optimized it. Now, how do we build a map of the environment from all of these data points?
So, localization and mapping, right? And I told you, you're going to see a little bit of mapping, or this is it.
Well, there's several different ways to represent an environment model, but I'm going to quickly introduce the binary occupancy grid. The idea behind it is that the environment is broken up into a grid of cells. If you believe the cell is occupied, you set the value to a 1. And if it's not occupied, you set it to a 0. Here, I'm assuming the entire environment is empty, and then filling in the cells where I believe there is an obstacle. But you could also assume the opposite, where the cells are all occupied and you set them to 0 when your sensor indicates that there's nothing there. You can see that with just 1s and 0s, we've generated a pretty accurate model of the rectangular room and part of...
So the problem with this is if you have these kind of tiles, even if it's partially occupied, you're going to block the whole thing, because there's no such thing as partially blocking a cell. Either the cell is blocked or not. So you are actually approximating. So if that blocks, that can result in a robot saying, I have no path to the goal, right? Because a partial coverage will block off both cells, whereas the TurtleBot 3 might actually be able to squeeze through. So the only way to avoid that is to go with smaller cell size. When you go with smaller cell size, what happens? The memory for the map increases. So again, I told you, life is full of these trade-offs, you have to take some pain in order to get some gain. So if you make the tiles smaller, then more memory is used in representing the map. Just imagine, if you have a tile like this, imagine how much memory you need for all of VIT. It's a lot, right? So that's what mapping requires. You need huge amounts of memory.
Of the circular obstacle. There are some holes, and we can fill them in by driving around a bit more, but overall it looks okay. Now, there's also probabilistic occupancy grids, where the cell doesn't have to be fully occupied or not, and instead there's a probability that it's occupied between 0 and 1. With this model,
So here, it's not 0 or 1, but it's a number between 0 and 1. based on how confident you are, there's an obstacle there. Now, how do you establish this probability number? It's because as the robot is driving around, the LiDAR is seeing the same cell multiple times, right? Because if you drive the robot around, it's constantly sampling the space above each cell. Either it's seeing nothing there, in which case it's saying there's nothing there, or it's seeing something there, right? So what they do is, they have a counter for each cell. And anytime they see something there, they raise the count. So they count up to, maybe they have 8 bits allocated to each cell, right? So 8 bits would be a maximum number of 255. So they'll count. I saw it once, I saw it twice, I saw it thrice, right? And the count might sit at 73. Now the LiDAR is no longer looking at that cell. So you leave it at 73, but that maps to a certain shade of gray. Now this is needed in order to detect moving objects. Suppose you have a dog that is walking across the road. You don't want to put the dog permanently on the map because it'll be there forever. So when the LiDAR doesn't see anything there, it's going to erase those cells. It's going to count down from 73, 72, 71. And LiDARs go very fast. It's not going to count as slow as me. It's going to count down rapidly, and it's going to eliminate that and say it's free. So that's how a typical map is stored. Even for self-driving cars, this is how they create maps. Because we have very rapid sampling of each cell. And that enables you to eliminate moving objects from the scene. You don't want a moving object on a map because it's moving. You don't want to put it permanently on the map.
You have full confidence in black and white cells, and everywhere else is some shade of gray, depending on your uncertainty. So there we have it, SLAM using pose graph optimization. Hopefully now you can see how a map of the environment and the pose of the robot can be determined simultaneously with this method. And now that we have an occupancy grid map, we can start the process of planning a future trajectory through this environment. The robot no longer has to wander around aimlessly, but can use this map to plan where it wants to go. And we're going to cover some ways to approach planning in the next video. But before I end this one.
So, Blessed, this is what I was telling you about. He's got the whole program there and goes through all the details of whatever he talked about. So, we're going to take a 5-minute break to give my throat a little bit of rest, and then we'll continue.